So now let's focus on chain rule for partial derivatives. Now even before that, let's do a quick recap. So in calculus 1, when we looked at functions of a single variable, we got to understand that the chain rule is used to find the derivative of composite functions. So for instance, given that y is a function of a single variable x, and then x is also a function of a single variable t, such that both f and then g are differentiable functions, and then y is said to be indirectly a differentiable function of t, so that we have the composite function y equals f of g of t. Now with this, we can use the chain rule to find the derivative of this composite function, and that is given by dy dt is equal to, we first find dy dx, and then we multiply that by dx dt. So basically, this is the chain rule formula for functions of a single variable. Now let's move on to functions of several variables, specifically functions of two variables. So assuming that we have a function z equals f of xy, that is, z is a function of two variables x and then y, and then we have x and y to be functions of t. So we have x to be equal to x of t, and then we have y also to be a function of t, that is y of t. Now with this, the composition z equals f of, now in place of x we have x of t, in place of y we have y of t. So the composition that is being expressed as z equals f of x of t, y of t, expresses z as a function of a single variable t. Therefore, we will need to find dz dt. We will need to find dz dt. And to find dz dt, we need four components. We need four components, which are, we need the partial derivative of z with respect to x, partial derivative of z with respect to y, the first derivative of x with respect to t, as well as the first derivative of y with respect to t. Now we can think of this as having a tree diagram. So with the tree diagram, we have z as the dependent variable that is on top, and then z is a function of two variables x and y, and then x is a function of a single variable t, y is also a function of a single variable t. Now to move from z to x and then z to y, since z is a function of two variables, to move from z to x we need the partial derivative of z with respect to x, and then to move from z to y we need the partial derivative of z with respect to y. The reason why we need the partials with respect to x and y is simply because z is a function of two variables, and then to move from x to t, because x is a function of a single variable, we basically need dx dt. Same for y, we need dy dt. Therefore, to find dz dt, dz dt is given by the partial derivative of z with respect to x times dx dt plus the partial derivative of z with respect to y times dy dt. Basically, this is the chain rule formula for functions of two variables. Now let's move on to functions of three variables. So given that w is a function of three variables x, y, and then z, and then x is said to be equal to x of t, y is equal to y of t, and then z is also equal to z of t. Thus x, y, and z are all functions of t. Then we can find the w dt, and that is given by, we have the partial of w with respect to x times the x dt plus the partial of w with respect to y times dy dt plus the partial of w with respect to z times dz dt. So basically this is the chain rule formula for functions of 3 variables. Now at this point, let's consider some examples. So let's take our first example. In our first example, we are going to use the chain rule to find z dt for z equals 3x squared plus 2xy plus y squared, where x is equal to 3t squared and then y is also equal to 4t. Now you realize that z here, the function z, is a function of 2 variables, x and y. Now we have z to be equal to 3x squared plus 2xy plus y squared, and then we have x and y to be functions of a single variable t. So x is equal to 3t squared, and we have y also to be equal to 4t. Now to find the z dt, we know that that is equal to the partial derivative of z with respect to x times the x dt plus the partial derivative of z with respect to y times dy dt. So we need to find partial with respect to x, partial with respect to y, the x dt, and then dy dt. So first, the partial derivative of z with respect to x means that we are going to differentiate this function, that is z, with respect to x. So in doing so, we are going to keep y constant. So for the first term, we have 3x squared. We differentiate that with respect to x, and then we have 6x plus, we are going to keep y constant. We differentiate 2x with respect to x, and then we have 2. So we multiply that by y, and that becomes 2y. Now because y squared is a constant, we differentiate that, and then we get 0. So we have our final expression to be 6x plus 2y for the partial derivative of z with respect to x. Now we know that x is equal to 3t squared, and then y is equal to 4t. So we are going to substitute the expressions for both x and then y into this results. So we are going to have 6 times x, that is 3t squared, plus 2 times y, 4t, and that is equal to, so here we have 18t squared plus 8t. Next we move on to the x dt. We are going to differentiate this function with respect to t, so that becomes 6t. And then we move on to the partial derivative of z with respect to y. We are going to differentiate this same function with respect to y. So 3x squared is a constant, it goes to 0 after we differentiate it, and then we move on to 2xy. We are going to keep x constant, and then we differentiate 2y, and thus we have 2. So that becomes 2 times x plus, we differentiate y squared, we have 2y, and thus we substitute the expressions for x and y in here, so that we have 2 times 3t squared plus 2 times 4t. So this becomes 6t squared plus 8t, and then we want to find dy dt, so that will be equal to 4. So finally, we are going to substitute these expressions in here, so that we have the z dt to be equal to partial of z with respect to x, that is 18t squared plus 8t. So you multiply that by the x dt, and that is equal to 60 plus, we have partial with respect to y, that is 6t squared plus 8t, and then we multiply that by dy dt, which is 4. So we are going to have 18 times 6, that is 108, and then t squared times t, that is t cubed, plus 6 times 8, we have 48, and then t squared, plus 4 times 6, 24, 24 t squared, plus 4 times 8, 32, 32t. So we can simplify this so that we have 108 t cubed, plus we add these two, 48 plus 24, that is 72, so 72 t squared, and then plus 32t. Therefore we have dz dt to be equal to the expression on the right hand side. So now let's move on as we take the second example. Now to example 2, we are going to find the w dt if w is equal to the square root of x squared plus y squared plus z squared, x is equal to cos t, y is equal to sin t, z is equal to tan t, and then t is given as pi on 4. So let's try this together. So we have w to be the square root of x squared plus y squared plus z squared. We can express this as x squared plus y squared plus z squared, all exponents, 1 over 2. Now to find the w dt, we know that is equal to the partial derivative of w with respect to x times the x dt, plus the partial derivative of w with respect to y times the y dt, plus the partial derivative of w with respect to z times dz dt. Now even before that, let's try to simplify these three, that is x, y, and then z. Now we know that x is equal to cos t, and then t is given as pi on 4. So automatically we have cos pi on 4, and then that is equal to cos 45. So if you want to evaluate this, cos pi on 4, your calculator should be in the radian mode. If you want to express pi in degrees, that is 180 divided by 4, and that will be 45. Therefore cos 45, your calculator should be in the degree mode. So cos 45 or cos pi on 4 is equal to 1 over root 2. Y is equal to sine pi on 4, and that is also equal to 1 over root 2, and then z is equal to tan pi on 4, and that is equal to 1. So we should take notice of these three. Now let's try to find the partial derivative with respect to x. So we have partial derivative of w with respect to x, and that is equal to, so considering this function, we are going to use the shortcut form of the chain rule to find the partial derivative with respect to x. So basically we are going to drop down the exponent. We differentiate x squared, we have 2x. Notice that we keep y and then z constants, so their derivative go to 0. We are going to repeat what we still have in the bracket, and then we are going to reduce the exponent by 1, so that is negative 1 over 2, exponent negative 1 over 2. So 2 cancels out 2, we are left with x. Now x here is said to be 1 over root 2, so we have 1 over root 2 times x squared, that becomes 1 over root 2 all square, plus y squared 1 over root 2 all square, plus z squared, which is 1 square, all exponent negative 1 on 2. So we have this to be 1 over root 2 into bracket, 1 square is 1, root 2 square is 2, plus same applies here, and then here we have 1. So this becomes 1 over root 2 times half plus half is 1, plus 1 is 2, so 2 to the power negative 1 over 2. So this becomes 1 over root 2 times, now because we have a negative here, it suggests that we have 1 over square root of 2. So this finally becomes 1 over 2, because square root of 2 times square root of 2 is equal to 2. Therefore, the partial derivative of w with respect to x is equal to 1 over 2. Now let's move on as we try to find the x dt. So we have x to be equal to cos t. Therefore the x dt is equal to negative sine t, and that will be equal to negative sine pi on 4, and that is equal to negative 1 over root 2. So this is the x dt. Now let's move on to partial derivative of w with respect to y, and that will be equal to, so for this same function, we drop down the exponent, we differentiate what's in the bracket with respect to y. We have 2y. We are going to repeat what we have in the bracket, and then we are going to reduce the exponent by 1. So this is equal to, so 2 cancels out 2, we have y, and then y here is 1 over root 2. So we have 1 over root 2 times 1 over root 2 all square plus 1 over root 2 all square plus 1 square. So we can basically ignore all those processes and then simply have 2 inside the bracket, exponent negative 1 on 2. So this is equal to 1 over root 2 times 1 over root 2, and that is equal to 1 over 2. So you have the partial with respect to y also to be 1 over 2. And then for dy dt, we have y to be equal to sine t. So dy dt becomes cos t, and that is equal to cos pi on 4, and that is 1 over root 2. So that is dy dt. Now for partial derivative of w with respect to z, for this same function, we drop down the exponent 1 over 2, we differentiate z square, we have 2z, we have x square plus y square plus z square all exponents negative 1 over 2. 2 cancels out 2, we have z to be equal to 1. So 1 times, now notice that x square plus y square plus z square is what gives 2. 2 raised to the power negative 1 on 2. So that becomes 1 times 1 over root 2, and that is equal to 1 over root 2. So that is the partial derivative of w with respect to z. Next, we need to find the z dt. So we have z to be tan t. So the z dt becomes sec square t, and that will be 1 over cos square t. Now cos t is said to be 1 over root 2. 1 over root 2. So finally we have this to be 1 over root 2 all square, simply because of the square here. So this becomes 1 over 1 square is 1, root 2 square is 2. So that's finally going to be 1 times 2 over 1, and that is equal to 2. Therefore we have the z dt to be equal to 2. So finally we have the w dt. So the w dt, and that's equal to partial with respect to x, we had that to be 1 over 2 times the x dt, that is negative 1 over root 2, plus partial with respect to y, that we had 1 over 2, also times dy dt, that is 1 over root 2, again plus partial with respect to z, that also we had 1 over root 2, also times 2. Now notice that this plus that is equal to 0, and then we have this to be 2 over root 2. Now because we have the denominator to be a set, we need to rationalize that. Therefore we have the w dt to be equal to, so here basically we are going to multiply top and bottom by root 2, so we are going to have 2 root 2 divided by root 2 times root 2 is equal to 2, so that becomes 2 goes here once, 2 goes here once, and then we have our final answer to be root 2. So therefore the w dt, the w dt is equal to root 2.